Hello, everybody. So, unfortunately, due to a low viewer turnout, I was unable to get the meeting started today, but that is 100% okay. I understand it's the middle of April break. I understand that math is probably the last thing we want to do right now, and I totally 100% get it. So, don't feel bad at all. I get it. So, as a supplement to the meeting that I would have had today, if more people had turned up, I'm going to record a video starting with here on Zoom, so you guys can kind of see my face doing what I would have done in the meeting in video and going through the entire thing, so people who couldn't make the meeting today and are still interested can watch it whenever they want, and they don't have to go to like an assigned meeting or anything like that. So this will be identical to the meeting that I would have hosted if more people showed up. The only thing that is going to be missing from this video is any possible questions that people could have asked if they came to the meeting. But I promise I'm going to try and answer as many questions that I think people would ask when I'm discussing what this course would look like. So for those of you who are unfamiliar with what I've been posting on Instagram over the past couple of days, or just don't know what I'm talking about, I'm considering doing a course in the summer that kind of runs the same way that class and school ran in the fall of 2020, full on Zoom, where I would go through the BC calculus curriculum, or I would go through kind of the fundamentals of calculus, applications of calculus, and any of the finer details and nuances as we go along. And this would be something I want to do because I really enjoy math. I've been self-studying for the BC calculus exam, and I've really been enjoying it. The exam is coming up, so if people are interested in knowing what score I got to see if it's like a credible thing to learn from me, I'm more than happy to provide that. But ultimately, the reason I'm doing this is not because I feel like I'm extraordinarily smart in math. It's because I feel like I really enjoy math. And as a result, I want to learn how to better teach math and give people the passion that I have for math. And that's what I'm looking for in this course. I've so enjoyed learning BC calculus. It's such an elegant subject. And if I can transfer that to other people, that would be a dream come true. So as a result, I'm still debating whether I would charge anything for this course. If I would charge anything, it would be not a lot of money at all, because like I said, I'm not doing this for a profit. I'm doing this because this is something I want to do and I really enjoy it. And if I did end up charging something and you come to a couple classes and you're like, okay, this isn't really something I want to do anymore, then I would give you all the money back. So there's no pressure whatsoever. The bottom line is, even though I'm running this like a class, from the fall of 2020, it is zero. What's the word I'm looking for? Zero obligation, zero commitment whatsoever. Which means it's not like once you sign up, you're stuck and you have to go through the entire course. If you start doing it and you realize, this isn't your thing, I totally understand, and you can drop out whenever you want. Because if you end up doing the course and you start going to these classes and it becomes more of a chore than something you want to do, I would hate for you to keep going, because I want this to be something that you enjoy. And if I'm making it something that you don't enjoy, that's not my goal at all. I would much prefer that you don't feel obligated to stay because of me, and I will not feel offended whatsoever at that. I understand that just math might not be for everyone. My goal, of course, is to try and convince people that math is very beautiful. So I've took multiple takes of this, so I'm not sure if I mentioned this before, but because this class is really oriented to the student, the time period is really flexible. And when I start getting more details for who wants to do this, and I start reaching out to people, the actual time period of this course will become more concrete. We could either do it over the whole summer and go slow, or a month and go quick, cover the fundamentals, cover everything, cover whatever you want. And that really depends on the people who are involved and want to do this. Like if you're gone for the entire month of July, for example, I'm definitely going to try and arrange the course to not be in July. Or if there's a lot of other people who can do it in July and you can't, I will definitely make sure to record videos so you can watch them. And if you're interested, that's another thing that I'm going to mention. What I'm going to do with this course is I'm going to record each lecture and post it on my YouTube channel, which I'm going to actually post this video to now. So if you're watching this video, it means you found my YouTube channel, and you can follow it. And I plan to post all of the Zoom videos on my YouTube channel along with any supplementary resources and practice things in the description of each video. So that way, even if you aren't able to make the lessons, or you end up going through BC Calculus through the school year and you need a little bit of help, you can watch my videos to kind of get a student's perspective on it. Because sometimes I feel like a student's perspective can be a lot more down to earth than a teacher's perspective. Not saying that teachers' perspectives aren't really good. They are really good, and oftentimes a lot more better than a student will be. But sometimes a student can phrase it in a way that you understand. So that is also another thing I want this course to be. It can be a resource, not just for the summer, but permanently on my YouTube channel. All right. So any other things that I want to mention? I think that's the gist of what I want to mention. I just want to mention that it's really flexible. It depends on, like, if anyone has any suggestions, it really, I will take them into consideration. This is a course for you guys, not for me, but for you guys. I want you guys to get the most out of this as possible. So with that, I think that goes for the general ideas of how I'm going to hold this course in the summer. And obviously things are subject to change. Things aren't solid right now. Nothing's set in stone. So any questions at all, please either comment down below or reach out to me on social media, Instagram, anything you want, and I will answer your questions. All right. So without further ado, I want you to get a feel for what the course would be like and how I teach. So what I've done is I've put together a very basic introductory calculus lesson that I want to teach you guys today on Zoom to kind of get you guys a feel for how I teach. If you guys have any suggestions for how I can better teach something, let's say I'm teaching something today and it's not clear, you guys can say like, hey, this part of the video wasn't 100% clear. Maybe you should try this. And I would really appreciate that feedback because I've never taught before. And I know I'm gonna be a beginner and I know I'm not gonna be perfect. So there's not a doubt in my mind that I'm going to mess up at some point. And I want you guys to help me better teach because at the end of the day, I want you guys to learn. And the better I teach, the more I'm achieving my want and my goal. So without further ado, I'm going to go out of this tab right here. And I'm going to go to our mock lesson Jamboard here, where I've kind of planned a little lesson for you guys today to kind of teach you my teaching style, how things would work and what each class would kind of look like. So I'm going to go through a very basic calculus topic with you guys, and actually kind of starts with the basics of calculus. Calculus actually begins with y equals mx plus b, which I'm hoping is something you guys are all familiar with. It's the equation of a line where m tells you the slope of the line or how steep the line is, and b tells you the y-intercept. So I'm going to go on to Desmos here. And I'm going to type in y equals mx plus b, and it's going to prompt me to add sliders where I can change the m value and change the b value. And you'll notice the m value just tells me how steep the line is, and the b value just tells me how high the line is when it crosses the y-axis, all right? So that is y equals mx plus b. And there's an efficient way to calculate the slope of a line or how steep it is using the formula that slope equals rise over run. And what that means, if you pick 2 points on the graph, let's say I'm going to pick this point where my arrow is right now and this point here, to calculate the slope or what m is, I take how much the graph goes up and divide it by how much the graph goes across, which is the same thing as saying rise over run. So I'm going to go to the next slide, and excuse my messy handwriting, but what this kind of looks like in a more mathematical sense is if you have a line and we pick 2 coordinates on that line. Let's say we have our x coordinate of 0.1 and our y coordinate of 0.1, and this is called a subscript, and it's just written below the variable to tell us that we're looking at the first point. So our x coordinate of the first point, y coordinate of the first point, and our x coordinate of the second point, and our y coordinate of the second point. And we know that the slope of the line is rise over run. So the slope is equal to the difference in the y coordinates divided by the difference in the x coordinates by definition, because the difference in the y coordinates is how much the graph rises vertically, and the difference in the x coordinates is how much the graph goes runs over that interval. All right. So I want to begin thinking of y as a function of x, which is something that you guys might be familiar with, you might not be. And if you've ever dealt with function notation before, you'll see things like instead of y equals x as a line equation, you might see like f of x equals x. And the general thing I want you guys to take away is that y and f of x mean the same thing, as I've written here. Let me delete this. However, I think f of x is more useful as that truly shows us how the height of the graph solely depends on the x coordinate. We know that when we have an equation, y equals x, y tells us the height of the graph, and x tells us the kind of where it lies horizontally. And we know from our definition of functions and lines that y is an independent variable and x is y is a dependent variable, apologies, and x is independent variable. And what that means is that y depends on the value of x. And if you have an equation like y equals 2x, you can see why this is true. Because if you know the value of x, if you know what our x coordinate is, you can just use this equation to figure out what the value of y is using basic algebra. So that's why we say y depends on x, because the value of x solely determines how high the graph is. And another way to say how high the graph is, or the y coordinate of a function, is, and we'll get to this in the next slide, is called the function value of the graph at x. So the y coordinate at a coordinate x is also called the function value at x. And now another way to visualize function notation and why it's useful is because it really shows that to get from x to y, all you're doing is doing something to x, your input, to get our output. So f of x equals x squared. What's that represent? What that's representing is you take your input, which is x, or the x coordinate, and you kind of put it in this box, which we're going to say is the function or something that's being done to x. And that box spits out x squared, which means that if you put in an input or an x coordinate, the output or the y coordinate that we spit out is x squared, meaning that our function is squaring inputs. So we say f of x equals x squared, meaning the function applied to x equals x squared. And the reason I like this notation the best is because, yet again, it shows you how y depends on x. The value that we get our output depends on what input goes into this box. And you'll also notice that the input that goes to this box, the thing that the box is doing to each input is the same. It's squaring it. So we had 2 as our x coordinate, 2 as our input. It go into this box, and we get out 4 because the box is squaring things, and our y coordinate would be 4. So written below, we say each coordinate is x comma x squared, because y equals x squared, or x comma f of x, because y and f of x are the same thing. So we have our input here, and then f of x, the function applied to x, is our output, which is the same as the y value. All right, back to lines. So using this, we said that the slope was the difference in y coordinates over the difference in x coordinates. And because y equals f of x, we can say that the y value at the second x coordinate is the function applied to the second x coordinate. And then the y value at the first x coordinate is the function applied to the first x coordinate. So we take those differences and we divide them by x2 minus x1. So I have a little example for you guys here. If y equals x plus 1, then f of x equals x plus 1. So what our box is doing here is just taking in inputs and adding 1 to it to get our output. All right. So then f of x2 is equal to x2 plus 1 because it's taking our input and adding 1 to it. And then f of x1 is x1 plus 1. It's taking our input and adding 1 to it. And if we expand this, we're going to get x2 plus 1 minus x1 minus 1. We have a plus 1 here and a minus 1 here, so that's going to be 0. So it's ultimately going to be x2 minus x1 over x2 minus x1. Because these are the same, we're going to get 1 as our answer. So the slope of this line is 1, and you'll notice that that directly corresponds to the m value here, because the m value in front of the x is 1. Awesome. So I want to go back to thinking of slope as the rate of change of a function. And the function we're dealing with in this case is a line. The function value means the y-coordinate, as I said before. So for example, y equals x plus 1, the function value at x equals 2 is 3, because f of 2, if we rewrite this as f of x equals x plus 1, f of 2 equals 3. Therefore, when we talk about rates of change of a function, we're talking about how fast the function value changes. So we're going to go back to Desmos and talk about it here. So thinking of slope as the rate of change of a function. Notice how if I have my slope as like 0.9, the function value, meaning the height, changes not kind of slowly, but kind of averagely, right? But if I increase my slope really high to like 10, the function value or the function changes very quickly. So we say it has a higher rate of change, and therefore the slope corresponds to a higher rate of change. And our rate of change just means the rate of change of the function, which corresponds to the function value. But what about stuff that's not a line, like f of x equals x squared, like the kind of function we were dealing with before, where it takes in inputs and the output squares them? And you'll notice that as we go farther away from 0 on the x-axis, we're squaring bigger numbers, so we're going to get way bigger y-coordinates. But if we are squaring smaller numbers, our y-coordinate is going to be closer to 0. So you'll notice that our graph kind of keeps going up and up and up and up and up like this. And in terms of a slope, we can say, well, it's kind of not steep at all here. It's very shallow here. But as we go up here, it gets steeper and steeper and steeper. So then the question arises, well, if it gets steeper continuously, right? It keeps getting steeper as you go up and up and up and up. So is there a possible way to calculate the rate of change of this function if it seems like we can't calculate the slope? Because how can we calculate the slope when the steepness is always changing? Well, then here's where we get introduced to a topic called local linearity, which is that curvy functions look like lines if you zoom in very far. And I'll show you what I mean. I'm going to graph f of x equals x squared. And you'll notice it looks curvy. But as I zoom in close to one point, very, very far, it begins to look like a line. So maybe I can calculate the rate of change at a point on this function by zooming in really far and then using our slope formula to calculate the rate of change. And that's exactly what I'm going to do. All right, so let's do this together. So I'm going to kind of formulate mathematically what we were talking about. So we know that our slope is equal to f of x2 minus f of x1 over x2 minus x1. So I'm gonna draw our very zoomed in parabola, which is the y equals x squared. That looks like a line, all right? And I'm gonna say that we're starting at some point x, all right? And our second point is a distance h away from x, all right? So then this x coordinate is just x plus h. So then this y coordinate for the second point is f of x plus h, because it's just the function. It's just you're taking the input and applying the function to it. And the function value at this point is f of x. All right. So the slope at this point is equal to f of x plus h minus f of x over h. And the reason is x2 minus x1 is x plus h minus x. We have an x here and a minus x here, so these end up going away, and we just get our h. Another way to think about it is our h value is our run. So it's rise over run, so it's just h left. All right. So we said, all right, that our function is going to look like a line as we get really, really small. All right. And how do we mathematically show that we're getting really, really small? Well, we could say, well, let's imagine that the two coordinates are getting really, 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 really close together, all right? And that will correspond to zooming really, really far into a function, all right? And we said that if we zoom in really far, it looks like a line. So maybe if we just take 2 points that are really close together, we'll get the slope at that point. And what that corresponds to is if h is the difference between the two functions, that corresponds to asking what happens to the slope as h goes to 0. And all that means is h gets smaller and smaller and smaller and closer to 0. So we're going to do this cool thing. I'm going to write it out. All right. As h goes to 0, the limit as h goes to 0 of f of x plus h minus f of x over h. All right. And what that means is we're asking what happens to this as h gets really small. Because we said, well, when h gets really small, we're going to get the rate of change at that point. All right. And we know f of x equals x squared, meaning that with every input that we take, the function is squaring it. So let's rewrite this as the slope equals the limit as h goes to 0 of x plus h squared minus x squared over h. All right. And let's do some algebra to rearrange this fraction here. So if you know how to square two terms, a plus b squared, you'll know it equals a squared plus b squared plus 2ab. All right. So we're going to rewrite this as, instead of x plus h squared, we're going to say it's x squared plus 2xh plus h squared minus x squared over h. And we're taking the limits as h goes to 0. All right. You'll notice there's an x squared here and a negative x squared here, so these two go away. And now we're just left with 2xh plus h squared over h. Now I'm going to factor the numerator here, and there still would be a limit term here, but I'm just going to deal with the fraction we have right now. So it would be h times 2x plus h divided by h. All right, and we have an h on top and the h on the bottom. And you'll know if I take a number like 2, for example, let's say that 2x plus h equals 2, and I multiply it by 4, and then I divide it by 4, all I'm doing is getting back to where I started. So in essence, multiplying by h and then dividing by h, they undo each other, so we can ignore it. We say that h and the two h's cancel each other out. Another way you can say is this is equal to h over h times 2x plus h. Because, you know, if you multiply these two together, you're multiplying the numerators and you get the same thing again. But h over h equals 1, because anything divided by itself is equal to 1. Now, you're probably thinking right now, Dylan, wait. We said h is going to 0. So wouldn't this mean we're dividing 0 by 0? And that's an excellent question. But in fact, we are not, because we are saying that h is getting close to 0, but it doesn't equal 0. We're saying h is very, very small, like 0.0000000 on and on and on 1. But it doesn't actually equal 0. That's why we can say that h divided by h equals 1, because it's close to 0, but it's not actually 0. So this leaves us with the slope equals the limit as h goes to 0 of 2x plus h. So then it's asking what happens to this expression as h gets really, really small. Well, when h gets really, really small, we can basically ignore it, and we're left with 2x. Which is amazing, because it tells us that the rate of change, or the slope of the graph at the x-coordinate x, is equal to 2x. All right? And this is called the derivative of x squared, which tells us how steep the graph is if we know the x-coordinate. And that is a very basic introduction to one of the main branches of calculus called derivative calculus, which deals with calculating the rates of change of different functions. And that's a very basic way that we think about calculating the slope of a function that looks curvy. We just zoom very close in, say, hey, it looks like a line, and then we calculate the slope. So I hope you enjoyed that. That was my mock lesson. Any questions, please leave it in the comments below. I would love to hear any advice about my teaching methods. If I'm going too slow, if I'm going too fast, if I need to explain things more, if I need to explain things less, anything at all, please let me know. Thank you for watching, and I will see you guys hopefully another time.